got signal? Okay, great. And we're up here in the middle of the clear cut, so sometimes it's hard to get signal, you know. Today's lecture is going to be more about shape, equilibria, and stability when it comes to planar systems. And hopefully this is the beginning of the end. It's some sort of like beginning of our or the end of our understanding of this, and we'll really have this stuff nailed down, and it will be so much fun. Okay, so to recall, we are dealing with a two-dimensional linear homogeneous differential equation system. Okay, all of our coefficients are constants. We have no extra functions added on, and everybody's got a state variable, and it's all pretty linear and all that fun stuff. Okay, now systems like this, they have one or two cases. Okay, they either have only one equilibria. Can you think of where it is? There we go. Only one equilibrium. So you think it's an xy coordinate that makes both of those equations 0 at the same time? Well, it would be at xy equals 0, 0. So the origin. Okay. If it doesn't have that, then, or, what the word or a line of them, and the line is of the form y equals negative a over bx. If that looks familiar, it comes from the linear systems lecture that we talked about. Okay, now having a line of equilibrium is cool and all, but it does make things tricky to be able to analyze. Okay, because your equilibria aren't isolated. So what I like to think about equilibria is it's a point in space where it is the one telling the trajectory where to go and what to do. You have a whole line of them. You can never draw a little circle around where you are and say, hey, that's the equilibrium who's driving. No, because it's just, you just got so many of them. So we're going to focus on this case right here. Okay, stick to the isolated equilibrium. Okay, so we know there's one equilibrium. It's at 0, 0. The next thing that we usually talk about is stability. Now, we've kind of been hemming and hawing around stability, but it has a great many cases, okay? And the stability, just like before, it comes from basically whatever that exponent on the E part of our solutions is, right? If we think about like one dimension, okay, x prime equals ax, my equilibrium point is x equals 0. And if A is positive, it's unstable. And if A was negative, it was stable, right? Because we either had growth away or decay down to it, right? Here, it's much more complicated because we've got these lambdas of the form trace plus or minus the square root of trace squared minus 4 delta all over 2. Specifically, there are 2 of them now. So we have stability in 2 different directions at once, and we need to understand what that means. Okay, so I like this little kind of tree type diagram here. Okay, we've got our lambdas, lambda 1 and 2. Okay, and there's 2 broad cases here. They can either be real valued or they can be complex valued. Okay. If they're complex valued, they're either alpha plus or minus I beta, or they're plus or minus I beta. So they're either complex with a real part or just purely imaginary, right? If there's real, we've got some different cases here. We either have 2 of them or one of them that's repeated, okay? And those need to be handled separately if we remember correctly. And in all these scenarios, there either is a 0 or there is not a 0 in both of those. And this is important, okay? 0 eigenvalues need to be treated quite a bit differently, because if we think about the 0 in the exponent there, it usually means no change. And if you have those things in a system, it can create lots of like weirdness going on. So basically though, all these different branches are things that we are going to have to explore in trying to understand, you know, what can possibly go wrong. And the first case that we are going to explore is two real eigenvalues where neither one of them is 0. Okay, that's the very first case we're at. All right, so that's our case number 1. And this is basically going to take up the whole rest of the video. So we have two real not equal to 0. Okay, that is the case that we are now in. That's where we're operating from. And this has delightfully different subcases. Again, think about one dimension. Okay, in one dimension, we had two cases. Technically, we had 3, but we had 2 cases where A is positive or when A is negative, right? A, negative. When A was positive, we had growth. With A negative, we had decay. Okay, here we've got a similar situation where we've got 2 different things that are acting like K, our eigenvalues, that can be positive or negative, either together or not. So, our first case that we will tackle is that lambda 1 and lambda 2 are both positive. The second case we'll tackle is where lambda 1 and lambda 2 are both negative. And then the last case we'll tackle is where lambda 1's negative and lambda 2 is positive. It doesn't matter which one you label, just that they're of opposite signs. That's the important part. Okay, now if we think hard about it, we're in the overall 2 real roots scenario. So that means my solution, my vector valued solution, will certainly look like this. Lambda 1t plus some constant, the second eigenvector, the second eigenvalue. All right, and both of those lambdas are positive. Okay, if I write this in component form, just sort of in general, I get something like this. And V11 is the first or top element of V1, and V21 is the first or top element of V2. All right, so when we, good Lord, is a lot of writing. When we write these down, there's an important thing to notice. Regardless of the numbers that are in front of everybody here, lambda 1 and lambda 2 are both positive, so both of these things are experiencing exponential growth. All right, so if I think of this on a time series, all right, if I start positive, I grow positive, and if I start negative, I go negative. And this is true for both x and y. So far, so good? Okay, great. So what that means, if we move to the next page, and I will fill in our case right here, we have 2 real with lambda 1 comma lambda 2 positive. That's the case we're in. Okay, remember I said we want to think about these things in the plane, because we have x and y interacting with one another. Okay, so x is always increasing away from 0. That makes sense. It's moving away from 0. So if x starts positive, it's going to keep getting bigger and bigger and bigger. If it starts negative, it's going to go to negative infinity. Just keep going that way, right? And if y starts positive, it's also going to keep getting larger and larger and larger. And if it starts negative, it goes away. Okay? So what we know is I'm moving like to the right and up, to the left and up, to the left and down, and to the right and down. But we don't really know how. I draw it in gray because we're thinking about it. Okay? I want to know basically like what is the general shape, because it could go like this. That's fine. Or it could go like this. These are all different options, and so I probably should have drawn them in different colors. But the important part is that they are all going away from the origin. We call that an unstable node. It's unstable because basically all flow goes away from it. And in order to try to get at which of these crazy, nasty pictures that I drew shape, let's look at an example. Okay. So I am going to start off with very simple examples, and I have other examples that are more complicated that I'll do in separate videos. Okay. So the first example I'm going to do, the coefficient matrix is 2, 0, 0, 3. Okay. Write down the system that applies to. Go ahead. Okay, you should be done. X prime is 2x. Y prime is 3y. Now, what's nice is this is completely decoupled. We actually know what the solution is. Oops, I forgot the initial conditions. There we go. Okay, we know it's exponential growth. Let's just pretend we don't know this. Just make pretend. I don't know what that is. Pretend. Pretend. There we go. Okay. So what we're faced with is I've got a system. We've got the coefficient matrix. We should find the eigenvalues. Okay. Whenever your matrix is only on the diagonal, or if it's upper triangular or lower triangular, meaning so that if off the diagonal there's at least 1 0, you could just read the elements on the diagonal for your eigenvalues to kind of prove that to you. 2 minus lambda, 0, 0, 3 minus lambda. I got to take the determinant of this, which is 2 minus lambda times 3 minus lambda minus 0, and this needs to equal 0. Hey, I can just read the roots right off it, and it's exactly those elements. Okay? So lambda 1 equals 2, let's say, and lambda 2 equals 3. Again, it doesn't matter which one you make 1 and 2. You just need to be consistent from then on. All right, so lambda equals 2 is the case I'm going to consider first. My matrix becomes 0, 0, 0, 3, not a 3. Boop. 1, because 3 minus 2. And this needs to be multiplied by a vector, and that needs to equal the 0 vector. Now, if you look, if we just go through with this first row and multiply it out, I'm going to get 0v1 plus 0v2 equals 0. There's no info here. This is not useful. Okay, so I want to use the second row, which gives me 0v1 plus v2 equals 0. And what this piece of information tells me is this right here means that v1 can be anything I want it to be. And this one right here means v2 has to be 0. So I'm going to choose the eigenvector 1, 0. Okay? All right, second part of this. Boop. Lambda equals 3. My coefficient matrix therefore becomes negative 1, 0, 0, 0. I have to multiply that by a vector, and that needs to equal the 0 vector. And so I get negative v1 plus 0 v2 equals 0. And right here, this is telling me that v2 can be anything it wants to be, and that v1 needs to be equal to 0. If I can make it anything I want it to be, I'm going to make it the easiest number possible. And so my eigenvector for this guy is 0, 1. Let's put this information together. Okay? So, to reiterate, I just did 2 pages, but whatever. Lambda equals 2, and that is paired with 1, 0. And lambda equals 3, and that's paired with a 0, 1. Draw some axes. Okay, this is my x-axis. This is my y-axis. Now let's make my pen quite a bit fatter. Not that much fatter. Okay, cool. And let's make it orange. And my highlighter is orange. This one's going to be for orange. Okay, first things first, I need to draw the 1, 0 vector. So that's 1 in the x direction. That is too fat. 1 in the x direction, and 0 in the y direction is right there. Okay, so my vector looks like this. Boop, boop. Okay, and in that direction now, if I think about how this is going into my solution, I've got a C1, V1, e to the lambda 1t. All right. And I did not make this nearly thin enough. There we go. This v1, that's what we've just drawn, the vector pointing in that direction. Okay. This c1 means that it can be any scalar of that vector. So it really just takes up the whole x-axis. And then if I look at this, this tells me as time goes on, am I growing or am I shrinking? So I dislike what has happened to this picture. There we go. That's my vector. And now my lambda is a 2, which means I'm growing, which means in this direction I move to the right or to the left. I just move away from the origin. Okay? Now if we choose a new color, let's go with red for the second one. Make it a little bit thicker. There we go. All right. Now, again, we've got a C2, V2, e to the lambda 2, t. Okay. The V2 is the vector 0, 1, which is just this guy right here. Okay. The C2 means I can scale it. So I can go all the way up here, or I can go negative and go down here. Great. So that is the straight line on which I can travel. And now this lambda 2 is a 3, which means I grow away from the origin. All right, so does this make sense? So on these axes, I'm just moving purely away in one of those directions. But now the big question is, and I'm going to go ahead and use like really tiny, do I look like this growing away? Or do I look like that growing away? Or do I grow away along a straight line? Those are the questions you have to ask yourself. Now, first off, if it was a straight line, that would mean X and Y are growing at the exact same rate. I can see over here, I've got a 2, and over here, I've got a 3, so it can't be the straight line. We can go ahead and get rid of the straight line. It can't be that one. All right. To be able to tell if I'm going concave up or concave down, what I'm going to do is I'm going to consider a very weird quotient. All right, the quotient I'm going to consider is, go away. Oop. So I've got a natural y-axis because the red here is exactly the y-axis. So I'm going to go e to the lambda 2t, and I'm going to divide that by e to the lambda 1t. That's a lambda. There we go. So I've got e to the 3t divided by e to the 2t. So I just get e to the t. Okay. As time goes on, we're moving from the tail of these solutions to where the arrow is. So as t goes to infinity, this goes to infinity. So kind of my rise over run is getting super, super steep. So I know as time goes on, my arrow has to be pointed like this. And then if I think about the limit as time goes to 0, this goes to 1. So I don't quite get flat. I kind of take off at an angle. And blow up to infinity. Now it's not perfect because this is just sort of like an ish style calculation, but it lets me know how I'm opening up and going away. And we can see that that node is certainly unstable. Cool. Any questions? Oh yeah, this is pre-recorded format. Okay. Next one. Case 2. And that was where both of my eigenvalues were negative. Okay. So if I think about it this way, let's go ahead and just jump right into an example. That 0 is drawn way too close to the 2. Right into an example. And again, I'm using incredibly simple examples to make all the calculations easy. I'll do more complicated ones later. So first off, lambda 1 is negative 2, and it has the eigenvector 1, 0. And lambda 2 is negative 3, and it has the eigenvector 0, 1. Okay, I mean, you can pretty much see that on the matrix. So now if I write my x and y axis, let's color these again. I'm just switching colors. That one's pink, and this one's green. All right, so going to the pink. First, I want to draw, I've got the solution here is C1, 1, 0, e to the minus 2t. All right, so the 1, 0, I draw that. Oh my God, why can't I see where I am horizontally? All right, so that's my vector, 1, 0. Now C1 means it could be any multiple of this. So I can go all the way over there, and I can go all the way over there. So it's the entire x-axis, right? Now what this guy tells me is I have decay in this direction. So I decay toward the origin. You guys see that okay? The next one, I draw the vector C2, 1, 0, e to the minus 3t. Okay. I can scale it by any C2, so I go up and down. And I decay toward the origin in that direction. Awesome. And so now the question we have to ask ourselves is, if I start anywhere else, do I decay inward in a straight line? Do I do it concave up, or do I decay concave down? That's the question we have to ask ourselves. How do we approach that when we're not on one of these perfect directions? Well, since -2 is not the same number as -3, we know we're not on a straight line. Okay? We can once again look at the ratio of things. Okay? So to do that, I think about my y direction is in the green, so I have e to the minus 3t, and I'm going to divide that by e to the minus 2t. This is the exact same as e to the minus t. Cool. So now, as time goes to infinity, e to the minus t goes to 0. So I know my arrow, my trajectory, needs to be flat by the arrowhead, not straight up and down. So I want it to be something like this. Whoop. That's beautiful. All right. And the limit as time goes to negative infinity of e to the minus t. So this is if I start at the head of the arrow and go back to where the trajectory starts, this goes to infinity. So it's got to be kind of straight up and down. So this is how my trajectories are flowing for this one. Okay. And we can see here that this, all roads lead there. So this is what we call a stable node. All right. We had an unstable node when both of the eigenvalues were real and positive. We now have a stable node when both of the eigenvalues are real and negative. Okay. We should also kind of figure these shapes of our trajectories here, because if I look at the green, all right, it has a stronger pull, -3, than the X, which has a weaker pull of -2. What I mean by pull is like e to the minus 3t decays faster than e to the minus 2t. So as I go, I should be changing in the y direction much faster than I'm changing in the x direction. So I should look something like this. Cool? I think it's cool. Next page. Last case for two real eigenvalues. So we have two real. Lambda 1 is positive. Lambda 2 is negative. Okay? We are once again going to do a little silly example here. X prime equals 2x, and y prime equals -3y. So I know that x equals x naught e to the 2t, and y equals y naught e to the minus 3t. But again, we're gonna, well, let's just pretend we don't know this. Okay? We write down our matrix. 2, 0, 0, -3. We can just go ahead and read off our eigenvalue eigenvector pairs of 2 with 1, 0. That is my lambda 1. And lambda 2 is -3 with a 0, 1. What does this look like on the plane? New colors, hooray! Dark green is the positive one, and purple is the negative one. All right. So if we take a look at this, I want to, what is my solution, the contribution to the solution from the dark green one? It is any constant times 1, 0 times e to the 2t. So I'm going to draw my vector 1, 0. I'm going to scale it by the constant, so it can go all the way up there and all the way down there. And then e to the 2t, God, I really hate that. It looks like I'm right on the line on my iPad. I have to draw like a good 1/8 of an inch above it. Now the e to the 2t means I grow in x away from the origin. Okay, so I'm moving outward. If we take a look at the purple one now, I've got any constant times 0, 1, e to the minus 3t. So I draw my vector. I scale it by any c2. And then in that direction, I'm decaying toward the origin. Okay. Now, from here, we don't really have to do any funky ratios or anything like this. To get at what the trajectories are doing, just think about it this way. Let's start right here. Okay, really close to that purple. I am more like the straight up and down trajectory than I am from the straight side to side trajectory. So I'm going to behave like that. So I'm going to start going down. But as I go down, I always have to move to the right. So that's what that trajectory would look like. If I started down here, I'd have to move up. Oh, but again, don't draw a straight line. Always have to move to the right. Over here, I can go up, but I have to move to the left. And over here, I have to go down, but I always have to move to the left. And so you can see it kind of... And this is called a saddle node. Saddle nodes are defined by two real eigenvalues, one of which is positive and one of which is negative. Okay, great. So the next video that's going to be coming up that you should watch after this, I'll do some complex, or rather, I'll do more complicated examples of these things, so it's not quite so simple as the axes are where my eigenvectors are. And then we are going to continue a bit later with some more of the cases of I'm hidden. There we go. Of what my eigenvalues are, if they're repeated or if they're complex or things like that. Okay, I gotta stop talking. Where's the button? Button.